So hi guys, this is Chetan and that is Darshan Patel. We are here to present a topic on characterizing private clouds, a large-scale empirical analysis of enterprise clusters. So this was written by Ignacio Cano, Srinivas Aiyar, and Arvind Krishnamurthy at University of Washington and Nutanix. So my friend Darshan will give you a brief introduction about what are private clouds and everything. So let's go.
Hey guys, so first we're gonna talk about private clouds. So what is private cloud? So the private cloud is a model cloud computing where the infrastructure is dedicated to a single user organization. Private cloud can be hosted either at an organization's own data center or at the third party like facility or via private cloud server provider who offers private cloud hosting services and may or may not also offer traditional public shared multi-tenant cloud infrastructure. So in private cloud, we do have dedicated servers, and cause the hardware is dedicated rather than multi-tenant, workload performance is predictable and unaffected by other organizations sharing infrastructure or bandwidth, and it comes with better security. Arguably, the most important benefit of a private cloud is security. So this is often the most cited reason for companies with private data concerns to like switch from a public cloud environment or in-house network to a private cloud. And in private cloud, the user has greater control over the security software in use and has over access of the data. But it does have its downsides to like mainly hardware related, and both hosted and managed private cloud solutions can have higher infrastructure and service maintenance costs. Like hosted private clouds involve server networking and data center investments. The motive, so what is the motive behind like writing this paper, like the research paper? So the main motive behind writing this paper is that there is no prior research on private cloud environments. All the previous work are mainly focused on desktop and public cloud environments like AWS and Azure and like Google Cloud. And the authors think that on-premise clusters are being used more and more with companies, security, legal constraints, and better service quality force companies to work in these areas. But we disagree with this claim as this paper was written in 2016 and pretty much so much has changed since then. Moreover, private cloud are often used by MNCs like Google nowadays. Of course, we think hybrid cloud environments are getting popular these days, and that's a topic for like another day. Uh, so what are the findings we did from the research? Uh, so what were the questions are answered in this paper? So what are the with what did we research? So we found out that what are the most common causes of failure, what kind of workloads are typically executed, what is the purpose of the storage, uh, what about CPU utilization, what effect do additional replicas have on data durability, and what drives companies to grow their clusters. So the findings from the research was made from Nutanix. So in this paper, they measure Nutanix private cloud installations at various enterprises. Approximately 2,000 clusters were examined. They developed a growth predictive model, and the research examines the dependability of hardware and application features in private clouds. They began by calculating hardware failure rates. Unlike previous measurement studies, their work investigates the failure characteristics of all essential components in a cluster node. They measured virtualization related defects and misconfigurations and assessed the storage and compute requirements of the cluster. Uh, like they described how the entire data set and the working set sizes of cluster changes over time and track the CPU and input-output requirements of the clusters over time.
I'm gonna take it from here. So the related work, the associated work can be like divided into two dimensions as they're shown in the paper. The setting one is one dimension, public clouds, enterprise settings, and consumer pieces. What is evaluated is the other dimensions such as hardware reliability and application workload characteristics such as like storage and computation requirements. So they narrowed their focus to the second dimension, and within each of its categories, they examined the context in which the measuring job was completed. So they observed that most of the prior measurement work and the most of the work done on public cloud and consumer PC settings, and very little measurements of private clouds and everything. So you can see the the table here. So they have the desktop settings and they have public cloud settings, and they have pretty much did with this, and there is no prior research on private clouds and private settings. Uh, and this is the index we are going through right now. So we'll go through context, we'll go to the cluster profiles, we'll go to the failure analysis, we'll go to workload characteristics, and after that we'll go to the modeling based on these measurements. So they built a durability model and cluster growth, which is a predictive model. We'll discuss that in the coming slides. So the Nutanix is a company basically. So Nutanix offers enterprise cloud systems. The cluster allowed with virtualized execution of applications as virtual machines and virtualized highly available storage through legacy file system interfaces. So this is a quick overview of Nutanix clusters. I mean, these are not present in the paper, but we did some analysis to help you understand how they operate and stuff. You can see these different type of clusters. You can see there's a different type of storage systems, like there's SSD and there is HDD, that is integrated computer storage, and you can see the operations interposed at hypervisor level and redirected to CVMs. You can see random replications of virtual machines migration, which are controlled by controller VMs, and there is a global view of cluster state. Uh, and coming to the clusters they use. So what is a cluster in cloud computing? I'll simply put this like it's a group of nodes hosted on virtual machines and connected with a virtual private cloud. So using the cloud allows for much of overhead involved in settings up a cluster to be entirely bypassed. So here we have 2,168 clusters in which there are 13,394 nodes. Each cluster is around like a size of 3 to 40, and which ultimately have 70,000 disk population. So this underscores the distinctiveness of the data set, so which has numerous little clusters versus few large ones. So many clusters in the sample are installed in a remote office branch office configuration, which is called a robo also. So some customers cluster their businesses. Um, so coming to the node configuration, so it is very essential to understand the fundamental configurations of various nodes that make up these clusters, which I just talked about. This will help you characterize the kind of workloads that can be executed on them. So we find that the sample consists of three primary node topologies, which are outlined in the table. So you can see config one refers to compute intense two nodes. So it's a compute heavy thing. It has 24 core operating at 2.5 gigahertz, whereas config 3 is primarily concerned with storage intensive nodes. It has like 30 terabytes of storage. So the basic configuration is represented by config 2. In contrast to earlier research that was like conducted on public clouds, where one of the most prominent features of clusters is the heterogeneity of machines. So in the case of private cloud clusters, we notice a much more humongous homogeneous pattern in the term of node configurations that are present within a cluster. So this is one of the most notable differences between two types of cloud clusters. Uh, so aside from the standard node configurations, the number of virtual machines per node and their sizes can assist characterize the type of applications that run in each cluster. So to that end, we divide our virtual machines into three categories. One is small VMs having a single vCPU, medium VMs that have 2 to 4 vCPUs, and large VMs with 5 or more vCPUs. So within this category, we notice that VMs lie in between 5 and 8 virtual CPUs for the large things. We'll come to distribution of VMs per node. So the figure here shows the average number of virtual machines per node as well as their size distribution among the clusters of varying size. So a median of roughly 21 virtual machines per node is observed. So the three nodes have the lowest virtual machine density and followed by 32 and 4 node clusters, in contrast to 16 node clusters containing an average of 32 virtual machines per node. So furthermore, the vast majority of virtual machines in each of the clusters are medium in size, which you can see in the next coming slides. So you can see there's like median of 24 and most of 4 CPUs are here, and there's a high density here and the low density here. So this figure is an average of virtual CPUs per virtual machine by cluster size. So the figure shows the average number of virtual CPUs per virtual machines for varying cluster sizes. So we observe an overall average of 2.6 virtual CPUs per VM with 32 cloud node clusters having the maximum of 3.6 virtual CPUs and virtual machines on an average. We'll come to workloads. So they surveyed with the Nutanix customers from their cluster sample and found the main 4 type of workloads that customers occur like in more than 90% of the clusters. So VDI that stands for Virtual Desktop Infrastructure, which is a process of hosting a desktop operating system within a VM that runs a centralized server. So VDI workload nodes typically have high compute and minimal storage use. So config 1 is the most common node configuration in this category, which is a compute heavy thing. And a server denotes server like workloads such as database servers, web servers, and so on. So in this type of workload, the most common node configurations are config 2 and config 3, mainly because it has more data with them. Config 3 has 30 terabytes of data, so server makes sense for them. And config 2 nodes are primarily used for light server virtualization, which is like 5 to 10 virtual machines. And config 3, as I said, can be used for denser server virtualization, which has like 1,520 virtual machine backups and file servers. And the third one is like a big data, like example applications goes like Splunk and Hadoop that analyze large volumes of data. So in this context, they can use config 3 nodes are most common, as the name itself says is big data. So I think that the config 3 will be most suitable for those. And others like they include like the remaining workloads such as IT infrastructure, custom applications like SharePoint, Link, and so on. So there's no clear dominating arrangement in this case. However, it's a bit of a mishmash. So it might contain different types of configurations. So they declared it as a mixed thing. So coming to the failure analysis, they examined the private cloud clusters constructed from enterprise-grade commodity components. So each of which has a chance of failing, potentially resulting in unavailability, performance degradation, or data loss. So the potential damage caused by such failures give us significant incentive to learn about them. Also in this section, they examine the failure statistics along a variety of parameters such as component return rates, so time to repair, and so on. So we focus on 2 types of failures in particular, hardware and virtualization. So other forms of failure such as transitory failure handled automatically by Nutanix software are left for the future. So as a result, without taking these kind of factors into account, it's a bit of a gamble, I would say, for this paper. And coming to the hardware failures, the distribution of hardware failures in the private cloud setting is demonstrated in the figure. So the data is based on the cases that we found earlier, and we can see the HDD failures are only 20% of total hardware failures, with memory issues accounting for the remaining 16%. So the other two components in the top four are SSDs, solid state drives, and power supply units. And yeah, you can see top three account for the around like 50% of hardware failures. Annual return rate. So there's component like a HDD, which has 0.676 of annual return rate, which is like 2 to 9% prior in the prior studies, and for SSD it's like 0.72. So what is annual return rate? So let me explain that first. So hardware component manufacturers define product dependability in the terms of annualized failure rate, AFR, so which estimates the probability of a component failing in a year. There's this guy called Schrodinger, if I'm not being wrong. This is from their reference. Noted that a customer's concept of faulty component may not match a manufacturer's definition for reliability estimates. So a disk provider identified no fault in 43% of customers' return disks. This work report annual return rate for customers reported component replacements. So the table shows ARR for four hardware components that make up over 60% of private cloud hardware cases. So these values are below industry norms, I would say. So HDD replacement rates are like what 2 to 9% before was, and while SSDs are like 4 to 10% in a 4-year period. This is not from this paper. This is what they referred from Schrodinger. And one fact, and 0.76 and 0.72 are the actual values that the guys from the paper actually got it. So one factor explains the statistics are quality. So their study focuses on high-end enterprise-grade hardware components. Other investigations use consumer hardware. So here you can see HDD may potentially be a superior because they aren't even at full capacity. Let's go to workload characteristics. So far, they have detailed the profiles of various private cloud clusters as well as their future characteristics. So in this part, they first focus on storage-related measurements before describing the usual computation I/O requirements observed in our private clouds. So finally, they provide a fine-grained analysis of workload characteristics utilizing some of the most typical enterprise cluster applications. So you can see usage over time seems to be stable and predictable. So 80% of the cluster use comes from storage, which has a mean of over 50% and a standard deviation of over which is like around 8%, and for CPU the mean is about 20% and the standard deviation is around 5%. So SSDs can generally maintain the working set. So 80% of node use is around 500 GB for the working set. Let's go to storage measurement. So the Nutanix cluster measurements provide us the information on enterprise workloads that are expected to differ from the consumer workloads or like transient activities conducted on public clouds. So furthermore, because of the storage devices accessed via virtualization layer, the instrumentation of the layer gives us a useful data about various elements of the storage workload. The characterized storage needs working set size and workload specific data translation reductions. So they also investigate the predictability in storage utilization among private cloud clusters. And yes, you can see the graph that represents total storage and used capacity per node, and the graph B represents working set size per node, and the red line is basically for the capacity, and the blue line is for the used storage thing. So coming to the storage requirements and data savings. So the figure A shows the cluster's total and utilizes storage capacity per node. So the 50% of nodes have 5 terabytes or less of storage, while 70% have less than 10 terabytes. So 80% of nodes have less than 4 terabytes of storage, and a third have less than 1 terabyte. The storage layer tracks the application's working set and caches it in SSDs when possible in order to lower the access latency. So the figure B shows the working set sizes across the nodes in all clusters. So 80% of nodes have 500 GB or less working set size. So the figure suggests that a typical 800 GB SSD on a cluster machine can handle most workloads like input-output in several of their sample clusters. The storage system is set to compress and deduplicate data to reduce storage overheads. So they want to know how compression and deduplication affect the corporate application storage. So they investigated the clusters using only compression, so 50% of the sample, and solely the dedupe, which is 25% of the sample, and both, which is like at around 16%. So Nutanix storage layer works underneath host file systems. Therefore, conversions are executed in 1 MB to 4 MB chunks. So the server and VDI workloads are a fraction of the before said 50%, 25%, and 16. So the compression always saves more than deduplication. So 60% of the clusters with compression enabled performing mostly server workloads save up to 40% of total space. So without compression, 10 terabytes of data could have been used. The 6B shows the VDI server compression. The figure B. The figure B shows depicts like VDI server compression saves more than VDI. So the server's 95th percentile is like 0.8, I guess, and VDI is 0.7. So workload doesn't differ much in deduplication savings. So 95 percentiles are 0.4 in less than 20% of clusters. So deduplication saves 20% or more. This is smaller than deduplication savings from a desktop file system study. So further, the clusters with both compression and dedupe enable save more than just one, but compression saves the most. So 50% of the clusters executing server or VDI workloads can save up to like 40% of the total consumed space when both techniques are operating. Whereas compression alone can save like 25 to 30% in the median situation. So overall, the dedupe savings and the cluster storage utilization measures have these effects. So given low disk use and tiny savings from deduplication may not be worth in the transformations expense, but as a failed nodes, data must be replicated on live nodes. Storage savings allow more capacity for recovery. So compression and deduplication allow more for application level data to be stored in faster SSD layers, enhancing the overall performance. So we'll have the storage usage predictability. So we want to know how storage utilization changes over the time. So they can estimate the business storage needs. So the figure here shows the mean standard deviation and 95th percent of all of total utilization for distant cluster across 8 months. So for 50% of clusters, mean storage utilization is at most 20% of total capacity with a 3% of standard deviation. So 80% of the clusters use at most 50% of overall storage capacity with a standard deviation of 8%. So at the 95 percentile, 80% of clusters consume 60% of total capacity. So customers tend to fill nodes predictably without chaos. And let's also look into CPU and input-output measurements. So this section describes sample clusters, compute and input-output needs. So we monitored, they monitored the cluster and time-based CPU usage. You can see that in the figure. It shows the CDF of cluster CPU used based on one month of minute level data. And cluster CPU consumption is an average of node CPU usage. So 80% of cluster utilize 20% or less CPU on average, with a 5% standard variation. So CPU is moderately high, I would say. So in only select circumstances, 90% of 95 percentile clusters use 40 or less CPU. So even at the 99 percentile, which is not displayed, 90% of clusters use 60% or less CPU overall. So CPU seems steady over time, so indicating that enterprise applications run on these clusters have a low need of elasticity, I would say. And the cluster software also, measures the number of input-output operations per second, which is IOPS in short form. So performed by enterprise workload. So the figure here shows the mean. The figure B shows the mean SD and the 95 percentile node IOPS over time. So 60% of the nodes do 1K input-output operations per second or fewer, with a standard deviation of 450. Although the standard deviation seems high relative to the mean, these numbers are far from the maximum number of IOPS supported by the nodes. So which simplifies the private performance capacity planning. So at 95% and 95% of the nodes perform at 6,000 IOPS. And we'll go to workload analysis. So they describe typical cluster workloads in here. So they analyze their distinguishing features. So these parameters are used to calculate IOPS, virtual CPUs, virtual machine sizes, etc. So the figure displayed the average number of virtual machines per node by workload. So the VDI workload, it's like Citrix, Zen Desktop, VMware Horizon, View, and like several other things, and have 26 VMs on average compared to 19 for other workloads. So, and Linux virtual servers run larger virtual machines than Windows. So this one runs smaller ones, typical server workloads, example like MySQL web servers. So these run larger VMs than VDI like apps. So the figure shows the medium-sized VMs dominate all the applications with an average of 2.5 virtual CPUs per virtual machine. So medium VMs have 2 to 4 virtual CPUs. So this figure indicates that the VDI workload have less virtual CPUs per VM, which is because of they have more virtual machines per node. So the figure B here shows the average IOPS per node across apps. So when developing a VDI environment, IOPS is a major factor, we could say. And VMware Horizon View conducts like 3.5 thousand input output operations per second. So while Citrix Zen Desktop executes like 2.5 thousand Citrix like IntelliCache as a caching proxy to decrease the backend input output. Let's go into the durability model now. So we are assessing the data storage durability, right? So we use observations from prior sections to estimate the chance of consecutive failures. When new nodes fail before the original failed nodes, data can be duplicated. This research helps determine the level of replication needs to assure data durability. There are like some assumptions: replication factor of 2, and random replication to replicate to random node, and the time required to create a new replica when a node goes down. So it's given by delta t, which is equal to n minus 1 into v. So the d is basically data to be replicated, and the denominator is data transfer rate, and it is the remaining live nodes. So P of delta t is equal to probability of node failures in delta t. So we decompose the overall period over which we want to provide the durability guarantee into sequence of interval, each of length delta t. So Q is data loss event when 2 failures occur within delta t time. So data could not be replicated, and on a yearly basis we consider all delta t intervals in a year. the replication factor employed in the cluster C is assumed to be RF2 in the analysis here. So we also assume the replication is done at random. So that is using RF2. So every piece of data saved on the node gets duplicated on one other random node in the cluster. So let n be the number of clusters in C nodes, and d be the storage of use of any nodes in the cluster C, and r be the network data transfer rate. The time t necessary to generate a new replica with data d when a node in cluster C fails is therefore given by p durability in this equation, and this is the number of intervals of delta t time in a year, and further let p delta t be the probability of a node failure in a delta t time. So we decompose the overall period over which we want to provide durability guarantee into the sequence of interval each length of delta t. So we define a data loss event of q in each interval as event where node failure f1 occurs and subsequent failure f2 happens within the delta t time of f1. So the data could not be replicated. So then the probability that there is no data loss in each interval has the following upper bound. So this is when there is no failure, and this is where there is exactly one node failure, and the remaining is just like the n-1 node that do not fail within the delta t time. So you can see the durability in the private clouds. So they will be using the models described before to characterize the data loss in the private clouds. So to calculate durability, we use the following measurements observed in our clusters. So A is failure rates, B is IO replication, and C is storage capacity utilized. So the figure here shows the CDF of their sample clusters data loss probability in log scale. So we notice that likelihood of data loss over a year for like 60% of the clusters is 106 for RF2, indicating a durability of 6 nines or higher. In the case of RF3, most clusters attain like 9s durability or higher. So given the failure model and storage characteristics, each new duplicate provides an additional 5 nines of durability. So the most clusters have 5 nines with RF2 and 10 nines with RF3. So the rule of thumb here, each additional replica provides an additional 5 nines of durability. And let's go through the cluster growth analysis predictive model. Yeah. So customers, they added nodes to their existing clusters on a regular basis. I mean, they do that typically. It's not a new thing. It happens every time. So given that cluster growth is a part of an enterprise conscious space capacity planning operation, so it would be fascinating to learn what drives such growth. So they use this machine learning driven approach. We'll be describing in the next slides. To do this, so they framed this research as a binary classification issue with the purpose of predicting whether the clusters will grow to the end and they also employed a linear classification named logistic regression model. So they introduced a sparsity by using L1 regularizers, since we are more interested in intervality of findings, like getting the most relevant predictive characteristics rather than achieving high accuracy. So they used 200 clusters that then grew at least once in a period of 8 months. So they have like 15,000 examples, and they are trained with different combination of features to understand which is important. So coming to the features, they built 3 sets of fundamental features based on general cluster size characteristics. So FC storage, related information. FS is like performance measures, and FP is performance measures. So the table shows a summary of features they are employed. So we look at 2 types of models, memory and memoryless. The former considers the previous examples to assist and anticipate the present ones. So whereas the later only considers current data. the number of steps they look back in the past determines the order of the memory models. And let's go through what drives the actual cluster growth. So one is cluster size, which upgrades from 3 to 4 node clusters. Next is storage needs, which is HDD usage, and compute needs, like a number of virtual machines. And the storage is more affecting the cluster growth than the compute, because people tend to use the storage more than computing power. So coming to the evaluation, I guess Darshan will give you what we want to be evaluated. Darshan,
Yeah.
uh, yeah, you can just go.
Uh, okay. Yeah. Thank you. So the evaluation which we made from the research paper. So the research paper was well organized, and it explains both the concept of private cloud concern and the method of prediction model in a clear and a concise manner. Uh, this paper this paper presented the first measuring study of enterprise private cloud computing on a big scale, uh, which allows for a better grasp of the challenges and benefits of private cloud computing. It also provides a comprehensive description of errors, constructs, and analytical model to demonstrate their views. Uh, so there are also several thoughts occurred to us while reading the article. So the first was the data set is confined to Nutanix customer data, which makes us question whether it is sufficient or even reliable. The second is the relative ordering of the feature weight is the only thing that researchers are interested in. The third one was during times of failure, the cluster growth for the prediction model ought to have considered the replication factor. It is worth noting that the performance characteristics such as the number of virtual CPUs or the load of the input-output I/O storage devices do not contribute significantly to the prediction accuracy of modeling growth. Uh, the the last one is as the paper was written in 2016, there were significant changes in the area of cloud computing, and moreover, private clouds are losing popularity, which is perhaps understandable given recent economic developments. So those were the evaluations which were made by by us while reading the article. So we came up with the conclusion of two different things, like large scale measurements study for private clouds and the modeling based on the measurements. So we built three sets of fundamental features based on general cluster size characteristics, FC, limited information. Table 1 shows a summary of the feature we employ. We'll look at the two types of models, memory and memoryless. The former considers previous examples of assist anticipate the present one, whereas the latter solely considers current data. And the amount of the steps will look back in the past determines in the memory models. So this was all the conclusions which was made by us while reading the article, like research paper.
I think that's our presentation, guys. Thank you. Thank you for listening until now.
Yeah, thank you guys.